This lesson is on Hess's law, which tells us that when we add chemical reactions together, we can also add the delta H's associated with them. So let's write that. When you add reactions, you can add delta H's. Okay, so let's look at a sort of generic example of that. And so let's say we have a reaction of A plus B going to C with an associated delta H in some arbitrary units of 20. And another reaction, C plus B, going to E plus F, and the delta H for that is 50 in the same units. All right, so because delta H is a state function, it doesn't matter how you get from the start to the finish. It doesn't depend on the path. So we can add up these two reactions. So to do that, we add all the reactants, we add all the products. So we have A plus B plus C plus B. That's all the reactants from both. C plus E plus F are the products. And since we can add those reactions, we can also add the delta H. Delta H's. So we get 70 in our units. We can also cancel things. We can cancel the C's, which are on both sides. And we can combine the B's. So we could say the overall reaction is A plus 2B goes to E plus F. So whether or not it goes directly from A plus 2B to E plus F, or whether it goes through this path, it doesn't matter. Delta H does not depend on path. It only depends on initial and final state. So the delta H is 70. A more general way of stating this is that the delta H for a multi-step reaction equals the delta H for the first step plus the delta H for the second plus however many steps you may have. All right, so and again, that is because delta H is a state function. And meaning it does not depend on the path. All right, a consequence of this is that if you reverse a reaction, write it backwards, you change the sign of delta H. If it was exothermic and you flip it around, it's endothermic, and vice versa. And if you multiply a reaction by some value, which we'll show examples of, you also multiply the delta H. So let's do an example with a real reaction. Okay, so we're going to try to find the delta H for this reaction, CO plus NO, getting CO2 and nitrogen gas. Okay, so we want delta H for that reaction, but let's say all we know is delta H for this reaction, which involves only carbon and oxygen species, and this reaction, which only involves nitrogen and oxygen species. So we'll have to try to put these together in a way that forms the reaction we want. Okay, so we can start out by saying, okay, we need CO, carbon monoxide, in the reactants, and here's a CO in the reactants. So we're going to use equation 1 as is, and I'm going to write that, kind of keep track of that by writing it over here. CO plus 1/2 O2 leads to CO2, and the delta H for that is negative 283 kilojoules. I'm going to kind of separate these. Okay, now we want, the next reactant we want is NO in the reactants, and we have a reaction where NO is a product, and not only that, but there's two of them. So we really want this reaction reversed. We want reaction 2 reversed, so that means we put a negative on it. But we also only want half of it, because we only want one NO, not two. So we're going to take 1/2 of the opposite of reaction 2. So I'm going to write this one backwards and divide everything by 2. That makes NO leads to 1/2 N2 plus 1/2 O2. Wherever we did the reaction, we got to do to the delta H. So the delta H is now going to be negative 1/2 times 181. Which is, well, I won't write that one part down. Okay, so, and then we can add these two reactions up, and when we do and cancel things, you'll find that you get exactly the reaction written above. The half oxygen on the product side cancels with the half oxygen on the reactant side, and you get the reactants you want. Okay, so then the delta H for that overall process is going to be the sum of these things, which is negative 374 kilojoules, and this was kilojoules. Okay, we can show this reaction graphically if we want to. We can do an enthalpy diagram, okay, with enthalpy going up, and we could say we start at some enthalpy value. We aren't giving it a number, but that's our start. And we go in 2 steps. We go negative 283, let's say it's this much, and negative is down. And then we go down another, this ends up being about 91. And so so this is our, whoops. This is our end down here. And we can also say that we can go directly from start to finish, and that would be negative 374. So you can go this path to 2 steps, or you can go all in one path. It doesn't matter. The net result is the same. All right, now you should try one. This is a more generic one with simple numbers. So we want the delta H for this reaction, and let's say we only know the delta H's for these reactions 1 and 2, so you should try to manipulate those in a way that the net result will be this reaction, and then manipulate the delta H's the same. So stop the video and do that right now. All right, so how do we proceed? What I would do is start with what we want. We want reactant A. We want one of them. So here's A, but it's in the products. So we need to reverse this reaction. So we'll do, and again, I like to keep track here so I remember what to do with delta H. We're reversing it, so we're doing A plus 4D leads to C. That delta H has to be opposite sign, but it won't be 1 anymore. That delta H will be a positive 200 in whatever units we're using. And then we'll see that reaction 2 we want to use also backwards because we want C in the products, or no, because we want 2B in the reactants. So we're going to flip it around, but we want 2 of them, not 1 of them. So we have to flip it around, make it B goes to 2D, but then multiply it by 2. So negative 2 times reaction 2 will be 2B goes to 4D. And we have to do the same thing to that delta H, flip it around so it's negative, and then multiply it by 2. So we get negative 600. Then we can add these up and cancel things. You'll see the 4Ds will cancel. One's in reactants, one's in products. So we'll get A plus 2B gives you C, and you can then add these. Since you added the reactions, you can add the delta H's, and you'll get a negative 400.